Hello. In this video, I'm going to be discussing three fairly simple derivative rules. The rules that tell you what the derivatives of the functions sine x, cosine x, and e to the x are. The rules themselves are fairly simple. Using them is fairly simple. Understanding why they're true gets a little more complicated, and that's the part that I had to really think about before I made this video. But with any derivative rule, there are three kinds of things that we could talk about in connection with that rule. We could talk about what's the proof of that rule? How do we prove it from the definition of the derivative? And this is the version of that definition that I like to use. It's the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x, provided this limit exists. Now, some people like to write it in terms of h instead of delta x. They use h as the variable that is approaching 0 in the limit. And it doesn't really matter one way or the other. Either way is perfectly fine. They're both commonly used. Another thing we might want to talk about is, why does the rule make sense? We can look at a formal proof, but that doesn't always give us a good feel for why the rule works the way it does, why the derivative is what the rule says it should be. So sometimes we can say something to get a feel for why the rule is true intuitively. And third thing we can talk about is, how do you actually use the rule? Let's see some examples of that rule in action. How do you actually use the rule to find derivatives of particular functions? So I'm going to try to talk about all three of these kinds of things for these three rules that this video is about. So the first two rules I want to discuss are the rules for the derivatives of the sine and cosine functions. So the derivative with respect to x of the function sine x is the function cosine x. And the derivative with respect to x of cosine x is negative sine x. So they are almost each other's derivatives. The derivative of sine is cosine, and the derivative of cosine is negative sine, the opposite of sine. And these rules assume that the x, the argument to the sine and cosine functions, refers to radians. So these derivative rules only work out so nicely if you're talking about the sine or the cosine of x radians as opposed to x number of degrees. And of course, we wouldn't have to use the letter x for the variable. We could say the derivative with respect to t of sine of t is cosine of t, and the derivative of cosine of t is negative sine of t. Or since the things that we take sine and cosine of are often angles, and we often use Greek letters like theta to stand for angles, we could say the derivative of sine of theta is cosine of theta, and the derivative of cosine theta is negative sine theta. So whatever the variable is, if we have the sine of that variable, the derivative is the cosine of that variable. But it has to be just the variable itself. It can't be some more complicated expression or function of that variable. So for example, the derivative of sine of x squared is not just the cosine of x squared, because there, what we're taking the sine of is not just the variable x itself, it's some more complicated expression, some function of x. So to figure out the derivative of the sine of something that isn't just x, we would have to use something called the chain rule, that I'm not going to be talking about in this video. It really deserves a video all its own. So let's go ahead and look at a couple examples of these rules in action. What's the derivative of the function cosine x plus 7x squared plus 3? In other words, if that's f of x, what would f prime of x be? Well, we already have some basic derivative rules that say the derivative of something plus something else is the derivative of the first thing plus the derivative of the second thing. And we know that the derivative of a constant times a function is the constant times the derivative of the function. The derivative of x to a power is the power times x to the power minus 1. The derivative of a constant by itself is 0. So using all of those rules For our derivative here, we get the derivative of cosine x is negative sine x, plus the derivative of 7x squared is 7 times 2, or 14 times x to the first power, plus the derivative of the constant 3 is 0. So we get negative sine x plus 14x for f prime. Okay, what about if f of x is 3 sine x plus cosine x? Again, remember the derivative of a constant times a function is the constant times the derivative of the function. So when we find the derivative of 3 sine x, we get 3 cosine x, plus then the derivative of cosine x is negative sine x. So altogether, f prime of x is 3 cosine x minus sine x. Okay, now what's the proof of these two rules? How do we prove that the derivative of sine x is cosine x, or that the derivative of cosine x is negative sine x? Well, the proofs involve some things that may look like magic if I don't prepare you for them. So this reminds me a little bit of how, like, in many of the James Bond movies, there's a scene early on where Q introduces Agent 007 to some fancy high-tech gadgets that he can use, and then later on in the movie, he'll be using those gadgets to get out of a tight spot or to do something secret agenty. And if we didn't know ahead of time that he had those gadgets, we'd be like, hey, that doesn't seem fair that he can just get out of that tight spot with that gadget. But since we know ahead of time that he has them, we're sitting there saying, oh yeah, I remember that. I wondered how he was going to use that. So the gadgets that we're going to be using in the proof that I'm going to show you are as follows. First, we will need these trigonometric identities for the sine or the cosine of a sum of two things. If you've taken a trigonometry class, you probably saw a bunch of trigonometric identities, including these. And even if you don't remember exactly what the identities are that you're seeing on screen right now, hopefully you remember that they exist and that the sine of a plus b is not just equal to the sine of a plus the sine of b. And the cosine of a plus b is not just the cosine of a plus the cosine of b. Sine and cosine do not just distribute over addition, but there is this somewhat more complicated identity that says what sine or cosine of a sum is equal to. So that's a gadget that we can use in our proof. And the other gadgets that we're going to need are that the limit as x approaches 0 of the sine of x over x equals 1, and that the limit as x approaches 0 of the function cosine of x minus 1 over x is 0. These two limits I did talk about in my earlier videos on limits. So I have talked about why these are true. And for now, I'm just going to accept that, yeah, these limits are what you see there on the screen. So if we ever encounter these limits, we know what they are. Okay, now here we go. And I'm not going to prove both of the rules. I'm just going to prove one of them because they both have proofs that work almost exactly the same way. And in lots of calculus textbooks, if you look at how the book presents the rule, they will show you the proof for the fact that the derivative of sine x is cosine of x. And then they'll say something like, okay, and then for the other one, the proof is left as an exercise. So just to be different, I'm going to show you the proof of the second rule, the rule about the derivative of cosine x being negative sine x. And then the other one, the fact that the derivative of sine x is cosine x, that proof works almost exactly the same way. So if you understand this proof, you could work that other one out for yourself, or you could look it up in a calculus textbook. So here we go. If we just use the definition on the function cosine of x, it tells us that the derivative of that function should be the limit as delta x approaches 0 of that function, but with x plus delta x in place of x, so the cosine of x plus delta x, minus that function just of x, cosine of x, all over delta x. So there's our difference quotient. And now here's where we're going to use the fact that if you have the cosine of something plus something else, that's equivalent to the cosine of the first thing times the cosine of the second thing minus the sine of the first thing times the sine of the second thing. So I can use that identity to rewrite cosine of x plus delta x as cosine x times cosine delta x minus sine x times sine delta x. So here the part of A is being played by x, and the part of B is being played by delta x. And now, in this numerator, where I got one thing minus another thing minus another thing, I'm just going to rearrange the terms a bit so that the two terms that involve the cosine of x are together. I'm going to write it as cosine x cosine delta x minus cosine x minus sine x sine delta x. Just rearrange the order of the subtraction there. And now, with these first two terms, I'm going to factor out their common factor of cosine x and pull that out. So I can write that as cosine x times cosine delta x minus 1 over delta x, minus, and then what I have left over here is sine x times sine of delta x over delta x. And now, as far as the limit is concerned, the variable is delta x. And x itself isn't going anywhere. It's a constant as far as this limit is concerned. And since the limit of a constant times a function is equal to the constant times the limit of the function, and also the limit of something minus something else is the limit of the first thing minus the limit of the second thing, I can rewrite this as cosine x times the limit as delta x approaches 0 of cosine delta x minus 1 over delta x minus sine of x times the limit as delta x approaches 0 of sine of delta x over delta x. Do these two limits that are inside the parentheses look familiar? Well, these are the gadgets that I introduced you to. We know that the sine of x over x has a limit of 1 as x approaches 0. And here it's just like the variable that's approaching 0. We're not calling it x, we're calling it delta x. But as anything approaches 0, the sine of that anything over that anything has a limit of 1. And what about this limit? The limit as something approaches 0 of the cosine of that variable minus 1 over that variable. Well, that limit is 0. So if we go ahead and put in those limits, we have that this equals cosine of x times 0 minus sine of x times 1, which of course simplifies to just minus sine of x. So that completes the proof. Now, why does it make sense that the derivative of sine x should just be cosine x? Why isn't it something more complicated or something relating to sine itself rather than to cosine? Well, for one thing, we know that sine of x is a periodic function, which means it sort of repeats the same behavior over and over and over again. The same thing happens when x is 0 as when x is 2 pi, 4 pi, 6 pi, and so on. So the derivative of a periodic function like that should also be a periodic function. It should have the same derivative when x is 0 as it has when x is 2 pi, or 4 pi, or 6 pi. Now that doesn't tell us exactly what periodic function the derivative ought to be, but it does make sense that it would be a periodic function like the cosine of x. And if you look at the graph, and in this graph the green curve is the sine curve and the blue is the cosine curve, but at every point on the graph of sine x, the derivative is cosine x, and at every point on the graph of cosine x, the derivative should be negative sine x. And if you remember that the derivative of a function is the slope of the tangent line to the graph of that function, that means that at any point on the green curve, which is the sine of x, you've got your x coordinate, you've got your y coordinate, which is the sine of x, and then the slope of the tangent line to the curve, to the sine curve at that point, is the same as the value of the cosine function at that point. So at points where the tangent line has slope 0 because it's horizontal, the cosine has value 0. It has y coordinate 0. At points where the tangent line to the sine curve has slope -1, the cosine curve has value or y coordinate -1. And in general, at any point along the sine curve, that's the green one, if you draw the tangent line, the line that is tangent to the curve at that point, the slope of that tangent line to sine matches the value or y coordinate of cosine. Now, why does it work out that way? Well, I don't know if I can really explain that or not. It does seem kind of magical, but one thing I can say that might or might not help is if you think about how sine and cosine are defined in terms of points on the unit circle. You're taking the sine or the cosine of an angle, and that angle, or that number of radians, represents how far around the unit circle you've gone. So I'm going to call it the sine or the cosine of theta so that I don't confuse that with the x coordinate or the y coordinate of a point on the unit circle. But as theta increases, that means you're going around the circle, and wherever you are on that unit circle, your x coordinate is the cosine of that angle, that theta, and your y coordinate is the sine of that theta. Now, the derivative rules, if you think of derivative as rate of change, that means that the cosine, which is the x coordinate, is the rate of change of the sine. The x coordinate tells you how fast the y coordinate is changing. And the sine is the opposite of the rate of change of the cosine. So the y coordinate tells you how fast the x coordinate is changing, but in the opposite direction. So if we go around the unit circle, wherever the x coordinate is largest, which would be right here where the x coordinate is 1, the y coordinate is increasing the fastest. If we get up here to where the x coordinate changes from being positive to being negative, the y coordinate changes from increasing to decreasing. If we get over here to where the x coordinate is most negative, that's where the y coordinate is decreasing the fastest. If we get to down here at the bottom of the circle, the x coordinate is changing from being negative to being positive, and the y coordinate is changing from decreasing to increasing. So if you think about what happens as you go around the circle, what happens to the x coordinate, which is the cosine, and what happens to the y coordinate, which is the sine, maybe you can convince yourself that, yeah, it makes sense that the x coordinate is how fast the y coordinate is changing, and the y coordinate is how fast the x coordinate is changing, but in the opposite direction. Now for the third of the three rules that this video is all about, the derivative of the function e to the x. And sometimes you'll see this function written as exp of x. It's just a different way of writing the same thing. So e is that special irrational number that's approximately 2.71828. And e to the x is the function that takes whatever number you give it for x and gives you e raised to that x power. And the rule is that the derivative of that function e to the x is e to the x. In other words, it is its own derivative. If f of x is e to the x, then f prime of x is also e to the x. Now, some of you might be thinking, wait a minute, don't we have a rule about differentiating something to a power, and you get the power times the thing to the power minus 1? Why isn't the derivative of e to the x going to be x times e to the x minus 1? Isn't that what that rule says it should be? Well, no, because that rule about the derivative of x to the n being n times x to the n minus 1 applies when you have a variable raised to a constant power. So the variable that you're finding the derivative with respect to is the thing that's being raised to a power, and then the power is just a constant number, like 2 or 1 or 12 or whatever. So when you have a variable to a constant power, like x squared or x to the 10 or x to the 1.1, that's a completely different kind of function than when you have a constant to a variable power, like 2 to the x or 10 to the x or 1.1 to the x, or like what we have here, e to the x. So these are exponential functions. Exponential functions are where the variable is the exponent. It's the power that some number, some constant, is being raised to. And in this video, I'm not going to talk much about those other exponential functions. I'll get to those in a later video. But for the function e to the x, the simple rule is that the derivative is e to the x. So what about if f of x is 10 times e to the x? Well, remember the derivative of a constant times a function is the constant times the derivative of the function. But here the derivative of e to the x is just e to the x again. So f prime of x would be 10 e to the x. So notice not only is e to the x its own derivative, so is 10 times e to the x, or really any constant times e to the x. And those are the only functions that work that way. The only function that is its own derivative is either just plain old e to the x or some constant times e to the x. So that's kind of what's special about the number e or the function e to the x. Okay, one more example. What about if f of x is e to the x plus 5x plus 3? What's the derivative? Well, we take the derivative of e to the x and get e to the x, plus the derivative of 5x is 5, plus the derivative of 3 is 0. Now, why does this make sense? Well, derivatives are rates of change, and exponential functions grow or change at a rate that is proportional to the value of the function. For example, if f of x is 2 to the x, the value of that function doubles every time x increases by 1. So if x goes from 1 to 2 to 3 to 4, 2 to the x power goes from 2 to 4 to 8 to 16. So it doubles in size every time x just goes up by 1. If you had 1.1 to the x, that would increase by 10% each time x increases by 1. But all of these exponential functions where you have some number to the x power, it increases at some percent, maybe 10%, maybe 100%, but some fixed percentage of the value of the function. So the bigger the value of the function is, the more it increases by, or the more that gets added on every time x just goes up by 1. So if you look at the graph of the e to the x function, the tangent line to the graph, which is the geometric interpretation of what the derivative is telling you, the tangent line has a slope that's equal to the value of the function, which is the y-coordinate. So no matter where we are on the graph of this function, y equals e to the x, the y-coordinate, which is e to the x-coordinate, and the slope of the tangent line are exactly the same. So here, where x is 1, y is e to the 1, which is the number e itself, approximately 2.718, and the tangent line there has a slope of approximately 2.718. Here, where x is 0, y is e to the 0, which is 1, and the tangent line has a slope of 1. And no matter where we are on this curve, either over here where the y-coordinates are just a little bit above 0, or over here where the y-coordinates get really big, the slope of the tangent line, which is the value of the derivative, is exactly the same as the y-coordinate. The value of the derivative is the same as the value of the function itself. Now, how would you prove this derivative rule? How do you go about proving that the derivative of e to the x is e to the x? Well, here we have a little bit of a problem, because to be able to prove things about e to the x, we have to know, how is e to the x defined? What is e to the x really? What do we already know about it that we can use in our proof? And when you first encounter this derivative rule in a calculus class, chances are you've probably never seen a completely rigorous definition of the e to the x function, or even what the number e is, because it's either defined in terms of a limit, which is a calculus concept, or in terms of some other calculus concept. If you look up on Wikipedia, characterizations of the exponential function, it gives several different ways that you could take as a starting point to define the function e to the x. And it lists the 6 most common definitions of this exponential function, e to the x, for real numbers x. So you could define it as this limit, or in terms of an integral, or an infinite series, or a differential equation, or things like that. But all of these definitions, all of these starting points, rely on some calculus concept. So how you go about proving things about e to the x kind of depends on what you start from as your definition of e to the x. What are you taking as your starting point? So I'm not going to give you a completely rigorous definition of the proof, because that's going to depend on how you have defined e to the x in the first place. And different people take different approaches to that. But I am going to at least show you what happens if you take the function e to the x and apply the derivative definition to it. So you take the limit as delta x approaches 0 of that function, but with x replaced by x plus delta x. So e to the x plus delta x minus e to the x over delta x. Now, e to the something plus something else can be broken up into e to the first thing times e to the second thing. So I can write that e to the x plus delta x as e to the x times e to the delta x. So if e to the x works the way the rules of exponents work, that's going to be true. And then here on top, we've got 2 terms that both involve e to the x, so I can factor that out and write this as e to the x times the quantity e to the delta x minus 1 all over delta x. And now, as far as the limit is concerned, e to the x is constant. It's delta x that is doing something, approaching 0, but e to the x is constant as far as the limit is concerned. So the limit of a constant times a function is the constant times the limit of the function. So this gets us to where the derivative of e to the x is e to the x times something, times whatever this limit is. And one of those definitions that I was looking at on Wikipedia kind of said, well, e to the x, or e to the x is the function that, if you put it in here, makes this limit turn out to be 1. For other starting points or other definitions of e or e to the x, you might have to do other things to figure out what's going on with this limit. But it does turn out that this limit is 1. If you draw a graph of the function e to the delta x minus 1 over delta x, just have y equal e to the x minus 1 over x, and look at what it looks like the y coordinate is when the x coordinate is 0, it looks like it's 1. If you plug in a value of delta x that's close to 0, you get a value that's close to 1. So it's at least believable that this limit does turn out to be 1. And that would mean that the derivative does turn out to be e to the x times 1, or just e to the x. And what I'm going to show you now goes way beyond anything that you would see in an introductory calculus class where you're still learning these derivative rules that I'm talking about in this video. But if you go on enough, and this is the kind of thing that you might see towards the end of a second semester calculus class, you would learn that the function e to the x can be represented by what's called a power series or infinite series. It's like a polynomial, but with infinitely many terms added together. And for e to the x, that infinite degree polynomial looks like this. It's 1 plus 1 over 1 factorial times x, plus 1 over 2 factorial times x squared, plus 1 over 3 factorial times x to the third power, plus 1 over 4 factorial times x to the fourth power, plus, and so on. You keep on having more and more terms in that same pattern. These exclamation points, in case you haven't seen those before, those are the symbol for a factorial that mean to multiply together all the numbers up to that number. So 4 factorial, for example, would be 1 times 2 times 3 times 4. 1 times 2 is 2, times 3 is 6, times 4 is 24. So, and this first term, this 1, we could even write that to fit the pattern as 1 over 0 factorial times x to the 0 power. Because 0 factorial and x to the 0 power are both defined to be 1. So if that's f of x, then what's f prime of x? What's the derivative of that thing that acts like a polynomial but with infinitely many terms? Well, if we take the derivative term by term, the derivative of the first term plus the derivative of the second term, and so on, the derivative of the constant 1 is 0. And the derivative of a constant times x is that constant times 1. And the derivative of a constant times x squared is that constant times 2x. And the derivative of a constant times x to the third power is that constant times 3x squared. The derivative of a constant times x to the fourth is that constant times 4x to the third, and so on. But look what happens when we take something like 1 over 4 factorial times 4. The 1 over 4 factorial means we have a 1 times a 2 times a 3 times a 4 in the denominator. But if we multiply that by a 4 in the numerator, that 4 and the other 4, the one on top and the one on the bottom, divide out. They cancel. And this reduces to 1 over 1 times 2 times 3, or 1 over 3 factorial. So 1 over 4 factorial times 4 simplifies to 1 over 3 factorial. Likewise, 1 over 3 factorial times 3 would simplify to 1 over 2 factorial. 1 over 2 factorial times 2 would simplify to 1 over 1 factorial. And the same sort of thing happens with every one of these terms. So this simplifies to just 1 plus 1 over 1 factorial times x to the 1 power, plus 1 over 2 factorial times x to the 2 power, plus 1 over 3 factorial times x to the 3 power, plus, and so on in that pattern, which is the exact same thing we started with as e to the x. So that kind of is another way of seeing that if you start with e to the x and you take the derivative, what you get is just, you get back your e to the x again. And there are also power series kind of like this for the functions sine of x and cosine of x. And it turns out that if you start with the series for sine x and take its derivative, you get the series for cosine of x. And if you start with the series for cosine of x and take the derivative of that, you get, well, basically the series for sine of x, but multiplied through by -1. So this is a peek at some of the more advanced stuff that you would see maybe towards the end of a second semester calculus class, Calculus 2. Now, so far we've talked in this video about the rules for differentiating sine x and cosine x and e to the x, and that followed a previous video about some of the basic derivative rules. So far, if you've followed along, you know how to find derivatives of lots of functions, but there are still some things you don't know. Still things I haven't covered yet in any of the videos I've made so far. There's something called the product rule that you would need to find the derivative of a product of a function that consisted of one thing times another thing. There's something called the quotient rule for if you need the derivative of something over something else. I already mentioned that there's something called the chain rule that is used when you want the derivative of, say, the sine of not just x, but something else like x squared. Or what if it's, you take the sine of x first and then you square that? And I told you the derivatives of sine and cosine, but what about the other trigonometric functions like secant or tangent, and their inverses like arcsecant or arctangent? And what about the other exponential functions, not just e to the x, but 2 to the x or 10 to the x, and their inverses like the logarithmic functions, log to the base whatever of x? So those all have rules that tell you what the derivatives are, but I'm not going to talk about that in this video, but hopefully I will be making more videos where I introduce you to some of those other rules. Thanks for watching. I hope this was helpful.